Our next speaker is Natan Bagrov from Deci AI. Natan is a team leader at Deci, and he has a master's degree from the Technion. I must say that I'm personally intrigued by this work as it applies techniques from meta-learning into the real world. So please welcome Natan.
Hi. Good day, everyone. I'm Natan, deep learning research engineer at Deci, also leading the algo team there. Can you hear me? I prefer to move, so I will talk a bit. Not טוב? בסדר, יאללה. Okay, great. In this presentation, I'll talk about YOLO-NAS, that is an object detection foundation model that was built using neural architecture search. This lecture is a bit different from the other lectures that you've heard and will hear because I will focus on the efficiency of the models that do the heavy lifting for all the applications. So a few words on Deci. So Deci is an end-to-end deep learning development platform. It is powered by our neural architecture search engine. And basically, we help researchers, engineers, and deep learning teams to reach to production faster with less barriers, with more certainty. And as I said, we do it with our neural architecture search technology. Apart from YOLO-NAS, that is open source and is out there in the GitHub repo, we also have YOLO-NAS Pose that is efficient and optimized for pose estimation. And if you are doing generative AI, and I'm sure everyone does it nowadays, we have our open source models in the Hugging Face. Unfortunately, I didn't put QR codes, so try to scan the link. Great. Before we talk about neural architecture search, let's ask ourselves, why can't we use one architecture, right? Why do we need different architectures? Okay, so this graph is the most important graph, at least for me. Okay, if we are doing our inference on a very expensive cloud instance, for example, I don't know, A100, H100, then basically we can use a big fat model that will be very accurate, but will be somewhat slower than other models. But because we doing the inference on the cloud, then we are fine with it, right? If we are taking some use cases that are that the inference is happening on the edge, for example, for I don't know, autonomous vehicles or mobile applications and stuff like that, we cannot use this big model, right? Because it's too slow and we will not be able to deploy it even to the hardware. And then we need to compromise on something that is somewhat less accurate, right? But is much faster and we can deploy it and use it. And this is exactly the orange dot here. And of course we have everything in between. For example, someone that is somewhat fast and like accurate, which is the red one. And the star up there does not exist, right? But we try to aim towards the stars, of course. Another important thing is that when we talk about accuracy, basically accuracy is a function of our data, right? If we will change the data set, then different models will be more accurate than the others. If we're talking about, for example, satellite images with very small objects, then it means that we would want to use specific models that capture better the information that is in a small receptive field than very deep networks that capture a very large receptive field, because we don't care about this receptive field. And the third thing, which a lot of people miss, is that when we talk about latency, we talk about a function of the hardware itself. Okay, so if I have a model and I'm using it, I don't know, on NVIDIA Jetson, and then I decide to move to a different hardware, for example, I don't know, Qualcomm Snappy or something like that, then the runtime of the model will be different, that's for sure. But also, if we are talking about the order of the models, it will also be different. There might be a model that runs really fast compared to other models on NVIDIA Jetson, but it will run very slow compared to the same models on a different hardware. Okay, so these are the things that we should keep in our minds when we design the solution or design the application. So now let's talk about neural architecture search. I assume everyone is old enough to understand this thing. So the way we do neural architecture search at Deci is basically Tetris. Okay, in Tetris we have our basic components or blocks, and we want to find the best combination of these blocks, right? So if we project it to the neural architecture search, these blocks represent a search space and some access of freedom that we will leverage in order to find the optimal architecture. For example, we can see that one block can say that we will use residual blocks, or if we talk about object detection, it can be PAN-NEC or FPN-NEC. It can also be like micro-architectural selection. For example, what will be the width of the ith convolution block, or it can also be a very macro-architectural selection if we talk about, let's say, segmentation, that you all know this unit, encoder-decoder, and it has skips. So we can choose whether we want a skip there or we don't want a skip there, okay? And eventually, when we define all these blocks, we have something to do the architectural search, right? And basically, we want to have something that is compact, optimized, and good-looking, and not something that is all over the place. Cool. Now let's talk about YOLO-NAS. So for the architectural search of YOLO-NAS, we used the familiar, I hope everyone is familiar with the YOLO architecture. It consists of three main parts, a backbone, a neck, and heads. And here, for example, you can see in this animation all the different architecture variations that you can achieve using the blocks from the previous slide, okay? And here, what is important is a trade-off between the complexity of your search space and the, let's say, and the performance that you'd reach using a search space of a certain complexity. Okay, for example, here you can see that we did not search for a different, let's say, a different parameters for heads, but we used a multiplier, right? On the other hand, we search for different types of blocks in the backbone, but not in the head. And in the neck, we search for different number of blocks, whereas in the backbone, it was the same number of blocks. Eventually, this search space consists of a lot of models, and to find the optimal one, we need to apply something that is not a vanilla search. Another thing is that if you look at the animation above, in order to put a point on the graph of accuracy versus latency, you need to construct the architecture, you need to benchmark it, and then you have your x-axis value, and then you also need to train it in order to achieve the y-axis value. Okay, so basically the YOLO-NAS is inspired by YOLO-V6 and YOLO-V8 architecture. We also suggested the quantization-friendly block because we will do int8 quantization later on. The search itself took about 5 GPU trainings, okay? And we trained the model with super gradients, which is an open source library that we have. And it also contains a lot of non-trivial off-the-shelf methods that will help you to achieve a better score or better accuracy when you do the training. If we look at the graph, so we can see that compared to other models, YOLO-NAS achieve more accurate results with about 30–35% faster. Okay. If we talk about int8 quantization, then we also reach to like, I don't know, twofold latency speedup, which is nice. Great. So We created YOLO-NAS to provide a foundation model for the community. It is pre-trained and is suitable to fine-tuning on most of the data sets. It is quantization friendly because we designed the search space in order to be that way. And we also wanted to show the importance of neural architecture search and the importance of hardware-aware models that are efficient for the specific hardware that you deploy. This is how you use it. Basically, 4-liner. And we're out of time. Thanks.